So hi everybody. So since today is the last regular class, I would like to talk about the schedule. So first of all, of course, the big date is May May 23. So we're going to have the final test or the final exam on that date. And we have it exactly on the same model as the midterm test. So this is 2 hours. Our standard time starts in 2:50, 10 to 3, and then 2 hours plus 15 minutes for whatever uploading or sending your file. And I guess, Ian, do you want to say more? I even don't know how it was technically done last time. Maybe you can say a couple of words for the audience here online and eventually for people who are going to watch the recording.
Well, I did a scheduled email to everybody who was signed up, and they all received the material at the same moment, and then
but then you can probably simply send it to everybody who was on your list. Now, okay, maybe some of them are no longer on the list, but okay,
of course somebody may receive it without doing the exam, but then it doesn't matter.
Yes. Yeah, exactly. Okay, and then they were sending it back to you.
They were sending it back to me. The only thing is that anybody who suspects they may be not on the list, they should certainly write to me. And if they write to me and they are on the list, it doesn't matter. So probably the best thing is write to me if you. It's a good idea to write to me if you want to do the exam. In principle, I won't forget those if they did it before.
Okay, so good. So that's the exam. And in case you have questions, please whatever, either ask them or write to me or write to Ian. Better write to Ian because he's really conducting it.
Sure.
Right. So
probably one very simple piece of information is if you are sitting waiting for the exam and at 14:50 Moscow time you didn't receive it, then it means that there is a technical problem. You should contact me immediately. Probably that's worth mentioning.
Okay, yeah.
Because this will all be done automatically by Gmail. So if you don't receive it, you should immediately contact
many different email addresses.
Yeah, it's okay. They know that. They have this.
Okay.
All of my email addresses are working for reception.
Okay, sounds good. So then, but so as I said, today is the last regular class, but there will be 2 more classes after the end of regular classes, after the final exam. So one of them will be about convexity theorems because it was promised, and today we don't cover convexity, so we're going to speak about convexity on the week after, and there will be one more aside class, and this will be about exotic moment maps, about because here in the course we were talking, or we continue talking about the standard classical moment map theory, but there are many branches of it, and we'll cover some branches, those that I know more about on this last class on June 6th. So, but though, of course, those classes, they don't make part of the program, they don't make part of the final exam because of the causality principle. And so that these are just some kind of seminars about those topics. So, and then I want to advertise one more thing. So we have now a break because there are vacations the next 2 weeks, and then the 3rd week I am away. But next week, all of a sudden, our local seminar in Geneva, the topic fits very, very well to what we were discussing last time and what we will be discussing next time. So it is by Michel Verne, who actually invented the localization theorem 40 years ago, and it is entitled Equivariant Volumes of Reduced Spaces. So it will be a hybrid seminar. So we'll send you a Zoom link next Monday, in a week from now. Also, I think, if I'm not mistaken, our Zoom links, they end. The last one is on May 23. So I also create new Zoom link for those last 2 classes. and we also send it, right? Since Ian, you have the list of emails, we can probably whatever publish it on the website and also send using this list of emails.
We'll work it out.
Okay, okay, perfect. So I think this is all I had to say about the organization. So, and so this said, we want to prove some properties of those Duistermaat-Heckman integrals today and discuss so-called Duistermaat-Heckman distributions. And so let me remind you our setup. As usual, we have a torus acting on a manifold M. We have an invariant 2 form, and we have a moment map. And let me say this is a compact Hamiltonian T-space. So today I have to tell you a little bit more about, so we dive back into Hamiltonian geometry and into symplectic geometry. And I'll tell you more about group actions today, and also, again, more on the day when we talk about convexity. So first of all, let's say, suppose that psi in T star a regular value. So today we focus our attention mostly on regular values of the moment map. When we discuss convexity, we'll also learn about critical values. So the values which are not regular. So it's a regular value of mu. So then mu minus 1 of psi is a submanifold of M. And the reduced space is a quotient of the level set by the T action. We know that it's symplectic, right? If things are good, it's a manifold. If the things are a bit less good, it's an orbifold. But as usual, we will focus on the case when it's a manifold. And for that, we assume that the T action is free. So these are assumptions which are in principle too restrictive. So normally people don't do it like that. But since so anyways, we are restricting our options to make presentation easier. So it's not essential. You can relatively easily get rid of those assumptions. So here is a fact, and today in some cases I'll give you an idea of how one proves things. Or sometimes I'll prove things. Sometimes I won't prove things. So so here is a fact. So there is an open neighborhood U of psi such that the preimage of U with an action of T and with a restriction of the moment map, which of course maps the preimage of U back to U, is isomorphic as a T manifold together with a map to the preimage of psi times U together with, oh, sorry, let me rewrite it like this. u times mu minus 1 of xi, together with a t action, and together with a projection to the first factor. So you see, it's a relatively strong statement. So on a neighborhood, so there is some neighborhood of the of a regular value, and then a neighborhood of the corresponding level set, such that basically I'm saying all the level sets as T spaces, they are the same. And this is just a direct product of my given level set times this image, this open neighborhood, some kind of small ball in the target space of the moment map in T star, right? So maybe let me do a drawing. So right, so here is my manifold M. So here, this is the target of the moment map. Here there is a map mu, and here is a fiber. And I'm saying that there is some kind of tubular neighborhood of the fiber, right? So I'm coloring it in yellow. And here there is some kind of ball. So the center of the ball is the image of my fiber, and there is some ball around it. And all the fibers, all the pre-images of points in that ball, they all look the same as T spaces. In fact, this is some kind of simple fact. And as usual, when we want to prove some kind of normal form of that type, we choose a Riemannian metric, let's say G. And first of all, of course, I want it to be T invariant, right? And then there will be some further condition that I will add later on. Like, just remember that in principle I can add conditions. So I will add another condition later on. Okay, but now what we are doing? So we are doing the usual thing. So suppose we have such a metric, and here is our level set, and from this level set we consider perpendicular vectors at each point, and we consider the corresponding geodesic rays. So these are and what we do, we normalize the velocity of those rays so as we move this constant velocity on T star. So so basically this gives you some kind of identification of all the different level sets nearby, and also it's T equivariant because your metric is T invariant. So so this means that everything
How is the velocity normalized? I don't understand why it is normal in some sense. What's the normalization condition?
Yeah, no, but I mean, okay, maybe let me say the following. So I consider, let's say, I first consider the identification, the standard normal form theorem, right, which would identify everything, which would identify my tubular neighborhood with a tubular neighborhood in the normal bundle. Okay, it is T equivariant.
Okay.
And after that, by the implicit functions theorem, I find those pre-images of the I find those pre-images or images of the level sets, and they are in one-to-one correspondence with my base, with the level set mu minus 1 of psi. So if I'm sufficiently close, the implicit functions theorem would guarantee that there are nice functions which are sending my level set mu minus 1 of psi to mu minus 1 of eta, if eta is sufficiently close to psi. Maybe, yeah, maybe let me better say it that way. So identify V, right, in and then so the implicit function theorem is giving me the maps between the level sets for eta small enough. And since
for eta minus xi small enough, you mean for eta close enough?
Yeah, for eta, yeah.
For eta minus xi small enough.
Right, for eta minus xi small enough. And since everything was T invariant, so this will be a T equivariant map. Right. Okay. Perhaps a remark. So this also tells us that M eta, which is by definition mu minus 1 of eta mod T, is isomorphic, diffeomorphic to the reduced space at psi. So I think at some point long ago, someone asked in the course how those reduced spaces change if you change the level. And here is the answer. Every regular value has a neighborhood, and in that neighborhood, all the level sets look the same, and all the reduced spaces, they look the same. You can actually identify them as manifolds, even though not in a canonical way. Right here, you see I'm using some kind of normal forms and implicit functions and God knows what. So especially the normal form, right? The normal form does not allow you to be sufficiently explicit. Okay, so here there are choices in this identification. Okay. So the next point. So let's consider the T action on the level set. So then we know, right, and then we say that Xi is regular. So then long ago, we proved the following. So we consider the map from the Lie algebra of the torus to the tangent space at some point. And we know that if Xi is a regular value, this map is actually injective. Of course, if we assume that the T action is free, it's for sure injective. Okay, so here is a claim or fact. So there is a one form, and then one. These values in this Lie algebra T, which is T invariant, and such that iota of xm of theta is equal to x for all x in T. So this is similar to Maurer-Cartan forms, right? So Maurer-Cartan forms are roughly defined in such a way when you consider a left or right action by translations on a Lie group. But now we consider some more general space. So maybe also let me recall, if you looked at the exercises for S1, we saw such forms for S1 actions. So there was a form theta in omega-1 of m S1, which satisfied the equation contraction with the fundamental vector field corresponding to 1 in the Lie algebra of the circle, theta is equal to 1. Right? So that we saw in exercises. Now, just a short idea of proof. So suppose I choose a basis of T. So then at every point M, EA of M, that would be the corresponding vectors sitting in Tm mu minus 1 of Xi, and they span a subspace. So then inside that subspace,
So maybe you should put an index capital M on this EA on the left-hand side, right?
so yes, sure, but I mean, how many indices can one put?
I understand, I just was mentioning.
Sure.
Fine.
Yeah, but I mean, yes. So, right, so they span a subspace inside that tangent space, and the tangent space carries a Euclidean metric because we have, we assume that we have a metric on our manifold. So then within that subspace, we can consider a dual basis with respect to that metric. So let me, so the dual basis of T of M, so the image of the action at the point M, so under the metric. under G. Okay, very good. So now theta is given by sum over A. And you can easily check that it satisfies all the properties and that it is independent of the choice of the basis, right? In principle, I can then choose another basis. In T, it would eventually change the dual basis, but the transformation is such that it's independent of the choices and satisfies the properties. Of course, it depends on the choice of the metric. For given metrics, eventually I can get different thetas. But right here, I only need the existence. So I don't claim this theta to be unique. We'll later on discuss a little bit what it is. For those of you who know what it is, it's a connection in the principal bundle, mu minus 1 of psi over the reduced space. So, sorry. Maybe I should say. Connection in the principal G acting on mu minus 1 of psi to m psi. Okay. Right. Now, again, something that you possibly know very well, or maybe maybe don't know. So actually, we have already seen it in the exercises. So here is another fact. There is a unique two-form on the reduced space with values in T, such that small f equal to d theta, so a two-form on the level set is a pullback of capital F. So, so that's our standard picture. We have the level set, T acts on it, and here there is a reduced space. Okay, so why is that? Again, a brief idea of proof. So in fact, one needs to show two things, that this small f is T invariant and that it is horizontal. So in other words, one should show that it is basic, and then this will mean that it's a pullback of some form on the base. So we know that theta is T invariant, and this implies that d theta is also T invariant. And so we also need to compute the contraction. So contraction of d theta. And you know, those calculations, they're always the same, right? So one uses the Cartan magic, right? That's the Cartan magic. Now the first term vanishes. That's because theta is T invariant. So only the second term remains. In the second term, we're using the property of theta. So this is minus d of the element x. But x is an element of the Lie algebra, and it's just a constant. It doesn't depend on any coordinates anywhere. So its Durand differential is 0. So that's because this is a constant. Right. Okay, so so this means that small f is basic. And then it's a pullback of some unique to form on the base. So this capital F is called the curvature to form. And so probably the last, or not the last, we still have 2 steps in our preparation, and after that everything will be solved. We'll be able to make conclusions. So the next step is let's consider, or let's define a 2 form. Let me call it omega naught, which will be a 2 form on this product. Remember, we had that neighborhood of the regular value, and now I consider a direct product of that neighborhood times the level set. And let me write down an explicit formula. So this will be a pullback to the level set, right? From here we have a projection to the reduced space. So I take a pullback to the level set of the reduced to form. So we know that mxi is a symplectic space, so mxi is the corresponding to form. Plus the following expression. So eta is again a coordinate on U. Xi is my base point inside U. And here I take theta. So just to say, right? So this guy is a 2 form on mxi, and I'm pulling it back by the projection. So so theta is a 1 form on mu minus 1 of xi with values in the Lie algebra, and eta minus xi is an element of T star. So the natural pairing is some real valued function, and I take the Durand differential of it. Okay.
And this is the value of omega 0 when the U component is eta.
Yeah, it is eta is the
I understand, yeah.
Yeah, eta is a coordinate on U. That's right. Okay, so it's a 2 form. So it is obviously closed, right? Because omega xi is closed since it's a symplectic form, and the second term is simply exact, right? So this is obvious. Here is a fact. Omega naught is symplectic, at least for eta minus xi small enough. All right, so why is it true?
Sorry, is D the D which belongs to M, or is it the D which belongs to U times?
Oh, it's D which belongs to U times mu minus 1.
Okay, yeah.
Right? So that's the manifold where I define.
Okay.
Okay. So let me rewrite omega naught on the different form. As usual, I outline the proof. Well, so let me write it like this. Plus eta minus psi d theta, right? Plus d eta theta. And let me rewrite one more time. Psi plus eta minus psi pi psi star f plus d eta plus theta. Okay, right. Now, first of all, right, this expression defines a two form on the level set. All the level sets are the same. Now, this is explicit in our presentation. So, so this omega psi plus eta minus psi times f for eta close enough to psi, that's again a non-degenerate form. And we know that this f is actually closed, right? That's because its pullback is small f, which is even exact. So maybe we should say here. Right. So capital F is closed. So in total, this expression for eta minus psi small enough, it defines a symplectic form on the level set. It is clearly closed and non-degenerate for eta small enough. The level set is compact since all our setup is compact. So then sufficiently for eta sufficiently close to psi, we cannot change the non-degeneracy of omega psi. Okay, very good. Now let me locally introduce coordinates. Let's say x1, x to m. So this will be coordinates on m psi, phi 1, phi k on fibers of the bundle, nu minus 1 of psi, and eta 1, eta k on T star. Kola, your mic is on. I don't know what
I'm sorry.
No problem. But just know what you're doing, right? Tearing some paper or doing something. Okay, right. So these are coordinates. Now we know that. Sorry. So this first term omega psi plus eta minus psi pi psi star f to the power m, let's say divided by m factorial, is equal to some non-vanishing function times the volume form in coordinates x1, xm. It also depends on, right? It also depends on eta. We're going to discuss how it depends on eta later on, but we know that this function is non-vanishing, right? So that's because it's symplectic. Now, we also know that thetas, right? Theta I. So these are basically those differentials of coordinates on the fiber. That we know because if we rotate the fiber, then the contraction is equal to 1 with the corresponding theta, plus possibly some one form which depends on axis, right? So there might be some whatever, some function of axis, some d-axis, whatever it is. Doesn't matter so much. So now let me consider d eta I wedge theta I sum over I to the power k over k factorial. So this is equal to product d eta I wedge d phi I from 1 to k plus some garbage. And this garbage, it includes some d-axis. Now, omega naught to the power n over n factorial is equal to this guy times that guy. This is because only the second guy, only the pin guy has d etas and d phis.
So is n equal to m plus k? 2m plus
n will be equal to m plus k. That's right. So only the pin guy has d etas and d phis. So this means that if you don't include this term, then the corresponding top degree form will be 0. So you have to include that guy. But then this means that you have to include the other guy to the power m, right? And then this means that all those dx's, they which are contained in the pin guy, they will never contribute. So this is equal to this c of x eta, which is non-zero, dx1 dx2m times product d eta I d phi I from 1 to k, and this is not equal to 0. So this means that this gadget is non-degenerate. So it's a closed non-degenerate form, at least for eta small enough. So I constructed a symplectic form on the neighborhood of the level set in this direct product. Now, the last step, the last claim, or the last observation. So we can choose the metric G. Remember, I left one choice open in the very beginning, such that omega restricted to mu minus 1 of psi would be equal to omega naught restricted to mu minus 1 of psi. And this would follow if I choose the metric in the following way. Right, I have the tangent space to the level set, and that guy has the omega orthogonal, which is it really true what I'm saying? No, I think I'm saying some nonsense. Okay, so yeah, perhaps I don't want to make it more precise, just because I think the argument that I wanted to tell you is not the right one. I would need to find the right one again. So it's relatively easy, as far as I recall, to arrange that. And then in any event, we proved some normal form theorems, but not so complicated one as would have been needed here. But it's similar in spirit. So by normal form theorem. So this is similar to Darboux and similar to the one for Lagrangian submanifolds that we proved before, but this one that we would need would be for coisotropic submanifolds. So by normal form theorem similar to Darboux, we can arrange the following. So there is a neighborhood, let me call it beautiful U, which contains mu-1 of Xi, and this is inside M, and then there is a beautiful V, which also contains mu-1 of Xi.
But you mean that U is open in M, right?
Yeah, right. In the space that we created. And a symplectomorphism V to U. So it's a usual setup of normal form theorems such that phi star omega naught is equal to omega. So in other words, not only level sets, they're all the same near regular value, but also I have a very, very efficient normal form. In fact, when I'm dealing with things near regular value, I can basically think that this is my symplectic form. So I can find whatever identification coordinates such that this becomes the symplectic form on the neighborhood of a regular value. And this is a very powerful statement. This is still a sort of easy statement. There are more general normal forms for non-abelian group actions, but I decided not to dive into it. You see, even here, kind of, it's a little bit of a shaky ground because we haven't proved the coisotropic normal form theorem. But this is a very similar idea to what we had before. So this is our normal form. And why is it very powerful? That's because it has many consequences. So let me list some of them. So corollaries of the normal form. So I think those normal form theorems, they were pioneered by Marl and Gilman-Sternberg. So there were two parallel developments in France and in the US. And we'll be interested in the following corollaries. First of all, in our presentation, we now have a very nice formula for a symplectic form on the reduced space at some level eta, which is near xi. So it's equal to omega xi plus eta minus xi times f. So you see f is the form which is obtained from geometry of the principal bundle, and otherwise, so that's a rather nice, rather beautiful formula on how the two form changes when you change the level set. Of course, one should say that here, remember, we made a lot of identifications, right? Or we made choices. So it's a beautiful formula in that normal form. But if you pass to chemology classes, so then basically nothing depends depends on choices, right? So this is an instance of the Chern-Weil theory of characteristic classes. So this F is independent of choices. So we're going to review it now, but it turns out that now all those choices, all these ugly things, choosing the metric, choosing this and choosing that, they no longer matter. Okay. Now it looks nice, but what are the practical consequences? So one consequence, which is very, very beautiful, is the following. Suppose that we are interested in a volume of the reduced space. So what is it? We know that all reduced spaces are the same, so we can say we integrate over m xi, and here we're taking omega xi plus eta minus xi f to the power m divided by m factorial, where m is half of the dimension of the reduced space, right? So then you see this is a polynomial in eta of degree bounded by capital M, right? So we take our symplectic form is linear in eta. Its m's power is at most a polynomial of degree m. So this means that this volume function is a polynomial of degree small or equal to m in the coordinates on the on T star, right? So this is sometimes you know there are many formulations of the Distrument-Heckman theorem. So this is one of them. So usually the theorem, I think, says that the symplectic form changes linearly. And then, of course, the behavior of the volume function is a corollary. So the volume function is a polynomial function. So maybe we just make one more conclusion. And remember, last time, in the end, we introduced the push forward of the Liouville measure under the moment map. And well, now we know how it looks like, right? So here we would have this exactly that form that we were discussing before. So omega eta to the power m over m factorial. And here we'll have a product from 1 to k d eta I theta I. And recall that here, if you want, we can replace theta by d phi plus garbage. And garbage depends only on coordinates on reduced spaces, so it doesn't contribute in the volume form. So this is then equal, you integrate over the fibers, and this gives you the volume of T, right? This is a d phi integral. So this is the integral. D phi's. Right. So times volume of the reduced space. So that's the integral over this omega eta, or over axis that we were discussing before. And here we have d eta, the Lebesgue measure, on T star. So that's the formula that I advertised last time. So of course, here we are always assuming that the T action is free, but if generic stabilizer is a discrete group inside the torus, then the volume of the fiber is smaller than the volume of the torus, exactly by the cardinality of gamma m. So then one needs to introduce this correction factor. So that's because the volume of the fiber is just smaller than the volume of the torus. Okay, very good. So so we spoke a lot today about regular values, but I want to, and basically, what is the conclusion? So maybe just to recapitulate, and then I'll tell you, we'll go into one particularly interesting case. So just to summarize. So we have the Dirichlet-Heckman integral Im of x, and by definition, it is equal to the integral of the exponential function under the Liouville measure. And now we know how to compute it. We have two different formulas for it. So one formula says that this is 2 pi to the power n times sum over fixed points. We always assume fixed points are isolated, right? And here, this product of linear functions, right? So this is the localization formula. And on the other hand, we now have an integral over T star. So here, volume of T. Let me call it gamma xi, this generic stabilizer volume exponential, right? Right. So we have two formulas. And in principle, the general idea of using those formulas is like that. So So this is supposed to be an easy part. Of course, who knows? You can invent examples where this is very difficult, but normally you hope, assume, or you consider examples where the fixed point set is an easy set and where you have control of the right-hand side of the localization formula. So what do you want to conclude? What do you want to find? So the difficult part is considered to be this. So you want to know something about reduced spaces. Reduced spaces, they might be difficult spaces. Who knows what they are? For instance, here we are trying to compute volumes of those spaces. So, so in general, use localization. To compute volumes. So that's normally how this pair of formulas is used. Of course, you see that the integral is more or less a Laplace or Fourier transform of the volume function. So then there are various techniques how you can take the expression for the localization formula, the right-hand side of the localization formula, and do the inverse Fourier or Laplace transform to recover the volume function. So that's a separate piece of technology, but already here we see, right, there is the equality between the yellow formula and the pink formula, and you can use the way you want, but normally you want to extract information about pink from the yellow part. Now, today I still want to tell you two things. We'll see that whether we have time. So one thing, let's say one thing is more general. The other one is a sort of very nice example. And let me start with the general stuff. And if we don't have enough time for an example, we'll reshuffle it to the convexity story. But just for your information, so there is actually a more general story. So suppose that alpha is a Cartan is an element of in Cartan complex, which is omega mt st star, and let's say it's a cocycle. So then, of course, alpha x for some given value of the Lie algebra element it satisfies an equation dx alpha x equal to 0 for all x in T. And of course, dx of alpha x exponential omega x is also equal to 0. So then we can use localization to compute new integrals, right? So I just take an integral over m alpha x exponential omega x, and this is equal to 2 pi to the power n sum over fixed points, and here alpha x of p exponential mu of px divided by the product of linear functions. Okay, that's good. So you see, this resembles from the previous page. This resembles the yellow formula. This is actually a localization formula. Let us also color it in yellow. Now, what about the pink formula? Is there an analog of the pink formula? And it turns out that yes. So let me draw a diagram. Again, for regular level sets, we have mu-1 of xi, which is embedded in M and which is projected to M xi. Now, there is a natural map from the equivariant cohomology of M to the equivariant cohomology of the level set. Now, if the action is free, the equivariant cohomology of the level set is simply isomorphic to the ordinary cohomology of the reduced space, right? So we get some kind of combined map going from here to there. It's usually denoted kappa xi. And there is a famous theorem due to Kernan, which says that kappa xi, which is also now called the Kernan map, is surjective. So we're going to discuss it in more detail when we talk about convexity, because we're going to talk about Morse theorem. But this map is surjective, and this is a very strong theorem, very surprising theorem, very interesting theorem. And in other words, given if you're controlling the equivariant cohomology of the ambient space, you surject on all cohomology rings of your reduced spaces. Okay, so now the pink formula. Here is a theorem, I believe, due to Dustermat, if I'm not mistaken. So, I alpha m of x. So this is an alternative formula. So this is an alternative formula for the integral. So it's equal to the integral over t star. And here there will be a function which depends on alpha, and some function of xi, dxi. So, and here is the formula for f alpha of xi. For xi, again, a regular value. So this will be again a volume of t divided by the cardinality of the stabilizer. And here, something very nice. So you see, so chi xi of alpha is a cohomology class on m xi. Exponential of omega xi defines another mixed degree cohomology class on m xi, and then we integrate the product of those two cohomology classes over the reduced space. So so that's the pink formula. Now you see, well, so the yellow formula tells us expressions for the integral, and the pink formula is telling us that this integral is a Laplace transform of some function, and this function it encodes all these numbers. But notice that by Curwen's theorem, chi xi of alpha is an arbitrary cohomology class. So this means that exponential omega xi chi xi of alpha is an arbitrary cohomology class on the reduced space. And this means that we basically now compute all the possible meaningful integrals on the reduced space, or how people say it, all intersection pairings, because I can now evaluate any integral. So all integrals on MXI. Of course, well, now the question is, in concrete examples, how efficient this calculus would be, but at least it gives you a machine, which if your combinatorics of computing integrals on the yellow side or localization formula, so then after that you need to recover the information. So you need some kind of efficient tool of taking Laplace Fourier transforms of exponentials divided by polynomials. So here there is still a lot of things to do, maybe more a little bit on combinatorics and analytics side, but still it's an absolutely like kind of wonderful tool, the equality of those two formulas. So I would like to end today's class with a small calculation, and we spoke a lot about regular values. So I will start speaking about singular values, and I will show you again one small miracle. So so this would go under the name of wall crossing. So, and my setup for this example will be the torus will be just one dimensional. It will be S1. As usual, the fixed point set will be a finite set. And in addition, I will assume that the values of the moment map at different fixed points are different. You will see why. So there is at most one fixed point by level set. Okay, so here is how it looks like. This is my manifold. Here there are some fixed points. The target of the moment map is simply a real line. So that's the moment map. And the images of fixed points under the moment map are exactly the critical values. Because remember, if we have a regular value, then this means that the fundamental vector field is everywhere non-zero, and then if it's everywhere non-zero, there is no fixed point. So so that's how it looks like. We have some finite number of critical values, and they split. So that's the image, right? So this is mu of m. The image of the moment map, if m is connected, is simply a segment, and there is some number of critical values, some finite set of points. So they split my segment into open intervals. So between two critical values, there is an open interval of regular values, right? Okay. So this means that our Dürstmann-Heckman function, now alpha is equal to 1, right? I'm just doing it for volumes, which depends on psi, is a sum. And let me denote them fs, s label my intervals. And here will be characteristic functions of those intervals. And recall that these guys are polynomials, right? So that's a Dürr-Heckman function or volume function. Right. Now we know that Im of x is equal to the integral over r exponential psi x f of psi d psi. Now I can actually compute that integral. At least let me write a formula and you complain if it is not clear. So I recall that fs are polynomials. So I represent them now. So I want to get rid of those polynomials under the integral. So I represent them as differentiations over dx to create some powers of psi. And then the integral over each interval I can compute explicitly. It will be exponential bsx, exponential asx divided by x. So I just computed the integral over each interval, and I took away this. This polynomial, replaced it by differentiation over x, and this differentiation over x gives me a polynomial in psi that I want. Now, of course, as plus 1, right, is equal to bs, where one interval ends, the next one starts. And I would like to collect now a term which would give you the exponentials with the same value of bs equal to as plus 1, right? So here, let me write it in the following way. So I redo the sum over s, and here will be fs d over dx minus fs plus 1, right, d over dx, and here will be e now there are only b's. There are no more a's because as plus 1 is equal to bs. Now let me do the following trick. I reshuffle the exponentials through the differentiation. Sum over s, bsx, and here will be fs d over dx plus bs minus fs plus 1 d over dx plus bs. And it acts now just on 1 over x. Okay. So, I was now working with the pink formula. But now let me recall that we also know the blue formula. Sorry, the yellow formula. And the yellow formula is saying this, right? So, right, so the localization formula is saying this. So that's the yellow formula. Right. So now you see both formulas are telling us that this is a sum of different exponentials, right? So these are exponentials, basically of the same values of the exponential of x times the value of the moment map at a critical point times some polynomial in 1 over x, right? But now the localization formula is a lot more precise. It is saying that up to a constant, this is always 1 over x to the power n. That's it. Now the pink formula is saying that this is some very complicated gadget acting on 1 over x. But since the two formulas are the same, this means that the polynomials should be the same, right? Or these one expressions in 1 over x should be the same. And so I made a small computation, and that's the last formula that I want to write. So it tells you that this fs minus fs plus 1 as a function of psi is equal to 2 pi over n divided by n minus 1 factorial product j 1 to n wpj minus 1 to the power n minus 1. I hope I didn't make too many mistakes. Psi minus mu of p to the power n minus 1, where in the pink formula, this mu of p, we know it is vs. So that's the wall crossing. So on each segment, on each interval, you have a polynomial. Those polynomials, when they come to an edge between the two intervals, to the when the two intervals meet, the polynomial is not the same on the other side, but the localization formula prescribes for you very, very precisely how this polynomial will change. So you have those walls in your domain, and jumping over the wall, you every time add something to your polynomial. Of course, f is equal to 0 when the preimage is empty, and here as well. And then you have a prescription for all the jumps. And maybe the last phrase. It works in a similar way for dimension of t bigger than 1. Of course, there the wall crossing will be more complicated. There will be more complicated walls. But you see here, I must say, it is just extraordinary, this formula, right? This interplay. You can basically now build your Dirichlet-Heckman function from the analysis that I gave you. So you no longer need to, so that gives you a very, very direct way of computing those volumes starting from the fixed point data. That's a little bit a partial answer to the question that we were asking before. So here I've done for you that work of inverse Fourier transform somewhat implicitly, and it gives those very beautiful jumping formulas. Okay, look, I think that's it for today. And as we discussed, it ends the regular part of the course. So I hope to see all of you in all those events that we advertised in the beginning. Sorry. No, what? Okay, let's kill it. Or how do we kill it? Oh, no. No. What? Sorry. Yeah, right. Okay. So, right. So I hope to see you at all those other events, but otherwise, in case we don't see each other, I kind of thank you for participation. It was a lot of fun to prepare this course and to teach it. Yeah, I don't know whether it was fun to listen it, maybe not, but well, thanks a lot.
I think we have benefited enormously. I hope the others think so too. I think we have, it's been great.
Okay.
Thank you very much too for this course.
Well, yeah, no, thank you. Thank you for participation.
Yes, thank you. I also have a last questions. I don't know if I can ask.
Sure.
Yeah, sorry, in the last page, our last formulas, you have this difference of this Fs,
Yeah.
this work-crossing formula. I mean, is there some like general type of difference equations that this function satisfies? I mean, some kind of difference equations or some.
No, I don't know. No, but this is again, in general, I have a domain which is split. We'll see it in this convexity discussion, but it is split by some kind of hyperplanes, right? So you have and then it splits. It is split into chambers. On each chamber, you have a polynomial, and then you need to glue those polynomials across the wall. For that, you need to know what happens with the critical points of your or critical submanifolds on that or which are on the preimage of that wall. I made very simple assumptions that on each, so to say, wall, now my wall is zero-dimensional. So I have one fixed point. So that's why my formulas are a little bit naive, those jump formulas, but nevertheless, the polynomial will change across each wall, and it will be, this change will be prescribed by the fixed point data on that wall. But you mean I wouldn't say this is I mean it's not quite if you mean that this is a difference equation for in S, I'm not sure, right? That's because in general it will be something like that. You will have some kind of domain, and in this domain you will have some kind of walls, right? And your function is piecewise polynomial, so it's polynomial on each of those subdomains. And each time you cross the wall, there would be a formula of the type like this, maybe a bit more complicated, but your polynomial will be some prescribed way how it jumps, depending on what happens on the preimage of that wall. So
Okay.
I wouldn't say it's so much of a difference equation, this
Okay.
wall crossing. Okay. Any other questions?
Sorry, maybe another naive question is that I also Googled that there are also this Artia-bot localization formulas. I mean, what's the kind of difference with our formulas, Vakhny formula?
No, the formulas, let's say, okay. So one thing is both Berlin-Verne and Artia-bot localization formulas. So they are in more general setup, right? You don't need the fixed points to be isolated. Okay, that's one remark. But otherwise, Artia-bot, it's a little bit philosophical. Like the formulas are always the same. So there are like not 100 species of localization formulas. So the localization formula, at least if you think of equivariant chemology, is always the same. Now, Artia-bot, it's a little bit different philosophical approach because they are saying that equivariant chemology is so equivariant chemology is a module of equivariant chemology of a point. And the equivariant cohomology of a point is a polynomial ring. So, and there is a natural map from equivariant cohomology of M to the equivariant cohomology of the fixed point set, right? So this guy is a free module. Over this polynomial ring. And Ati and Bot, they study the kernel and co-kernel of that natural map. So, and they prove that this kernel and co-kernel as modules of a polynomial ring are torsion modules. So you see that they have some kind of a little bit more algebraic approach, more conceptual and more algebraic approach to the problem. Then I must say I never looked at it carefully. I'm not sure. Surely they knew how to do it, but it doesn't occur as a very natural problem like integrating this exponential of omega x. Because in order so this guy is not, to be honest, not quite an element of HT of M. Right, it's some kind of exponential, so it's a mixture with degrees going to infinity. So, the approach that I presented to you was, of course, a little bit handicraft approach, but of course, the formula is always the same, but it shows that you don't need an algebraic approach for localization formula to hold. It's sort of more, a little bit more analytic approach. Of course, if you want to think of other coefficients, not real coefficients, then probably you need to think more algebraically. So in both approaches, there is some advantage, but the formula is always the same. So the only one that exists, that's the one that you saw in the course.
Okay, thank you.
Okay. Thanks a lot, people. Yeah, it's probably a good time to stop. So I don't know, Anfisa, as usual, a very brief checkup. If there are no further questions. So again, thanks a lot, everybody, and hope to see you soon.
Коля, ты тут.
Да, у меня не очень.
Я тут, да.
У меня не очень длинное сообщение, просто, ну, у нас вот кончились каникулы, так что теперь я думаю, что все, будем надеяться, что относительно быстро должно произойти. Но я думаю, что вряд ли еще что-то произошло, потому что вот люди сегодня только пришли на работу. Я надеюсь, после продолжительного отдыха. Вот. Ну, а я не знаю, у вас же тоже там, у вас теперь наступают, да, каникулы?
Ну, через неделю.
Несколько другого сорта каникул.
Да. Вот. Но у нас как раз прошлая неделя вся была такая, что там, ну, примерно никого нету, поэтому это не очень эффективно проверять было. Но, и да, не, они даже спрашивали, но им, конечно, никто не ответил. Вот, но будем надеяться, что теперь, ну, как я вам напишу, как только там будут какие-то новости, ну, и вам наш секретариат пришлет. Вот, слушайте, а вы там выяснили, куда вообще эти документы нужно подавать, что, куда, или это еще пока?
Нет.
Ну ладно, ну хорошо, когда дойдет до дела, я думаю, что... Вот. Ну отлично, здорово, будем надеяться, что это все скоро произойдет, и что, значит, все потом пройдет удачно. Ладно.
Ладно, спасибо большое.
До свидания.
До свидания.
Ладно, до свидания.